Let's just summarize everything we figured out about linear differential equations. So if you have an order n homogeneous linear differential equation, we saw that what we really want to find is a fundamental set of solutions. This is a solution, a collection of n solutions that are linearly independent. And we can check if they're linearly independent by checking that their Wronskian isn't 0. If you can find a fundamental set of solutions, then all solutions will be of this form, just combinations of your n solutions from the fundamental set. So you can choose any constants to come up with different solutions here, and every solution will be of this form. And that's for homogeneous linear differential equations, so we need to find a fundamental set. Now for non-homogeneous linear differential equations, we assembled a general solution in a different way. So we had to somehow find a particular solution, so this is just one single solution to the non-homogeneous differential equation. It could be any solution at all, as long as you can find one. And also we had to find the complementary solution to the associated homogeneous differential equation. And then the general solution is the complementary plus the particular. And again, you can, in the complementary solution here, you'll have all of these constants that you could choose, right? And you can still choose any constants as long as you remember to add that particular solution. So the distinction between homogeneous and non-homogeneous linear differential equations is actually the same as the distinction between homogeneous and non-homogeneous linear equations, just algebraic equations. If we look at a two-dimensional example, so if you have a homogeneous linear equation in two variables, it would look like this. So some number times x plus some number times y equals 0. And what would solutions to that equation look like? Well, it's going to look like a line, but because the right-hand side is 0, it's going to be a line through the origin. Now, on a line through the origin, if you have any solution, if you have any two solutions, like this red one or this green one, if you add them together just by stacking them on top of each other, you get another point on the line. And that's why for homogeneous equations, sums of solutions are solutions. It's very much the same as for a linear algebraic equation. For a non-homogeneous equation, well, for an algebraic equation, that would look like ax plus by equals c. And this c here, this means you would get a line parallel to the first one, but it wouldn't go through the origin. It would be up here somewhere. Remember, to the homogeneous equation, we had this dotted line down here. So a particular solution in this situation is just some point on the line. So there's y sub p. Okay, and this dotted line here, this was the complementary solution. And if you take your particular solution and then add solutions coming from the complementary solution, you can tell it traces out this whole line of solutions to the non-homogeneous equation. So this is exactly the same for differential equations between homogeneous and non-homogeneous. For non-homogeneous equations, first you have to get yourself sort of into the right space of solutions by having a particular solution, and then move along the homogeneous solutions to get all of the solutions to the non-homogeneous equation. All right. So our general strategy for solving linear differential equations is find a fundamental set, and if it's a non-homogeneous equation, find a particular solution as well. Then we can just combine them in these ways and be sure that we have all solutions if that uniqueness theorem applies, which it usually does. But this strategy for solving linear differential equations isn't much of a strategy, because so far we don't actually know how do you find a fundamental set for a homogeneous equation, and for a non-homogeneous equation, how do you find a particular solution? So we're going to have to spend some time figuring out how do we come up with these solutions so we can actually assemble them in the way that we know that we need to.